Okay, so the tangent ratio. Graphing the tangent ratio is a little bit different than the sine and the cosine, and you'll see once we get into the values of theta why that happens. So just a couple of refreshers. In a right triangle, our trig ratio that we use is opposite over adjacent. When we're dealing with it in a circular definition, so when we think we have the right triangle ratio is when we use SOHCAHTOA. Circular definitions when we use that Sir-Kixer-Tix, so that's the y over the x. And then if you're thinking of sine and cosine, if you remember y in a circular definition is the same as the sine value, and x is the same as the cos value. So 3 different ways of writing the tan ratio, but they all mean the same thing. So in a unit circle, by definition, where the tangent of the circle intersects the terminal arm is where we have a tangent line. So if this is our angle theta here, and this side here then is our tangent, because this is our tangent, so this would be the tangent of theta. This point right here, because we're dealing with the unit circle, would be at 1 tangent theta. That's what we would consider our coordinates. If we look at this by definition of a slope where we have rise over run, tangent of theta is equal to our opposite over the adjacent. Slope is equal to rise over run. So if we think about this, if we're looking at our tangent, we have our rise, which is our tangent, over our run, which is our rise, which is our y value, and our run, which is our x value. So in this case here, if we're looking at that triangle, we would have y over x to calculate our rise over run, which works out to be the same as opposite over adjacent. So that's where all that comes in. When we're dealing with the tangent and when we're dealing with the graphing of it, you have to remember the unit circle, what our coordinates are for these different measurements, I guess I want to say. So on the unit circle there, we know that this coordinate here would be our 1, 0, if we're looking at 0 and 2 pi. This coordinate here is at 0, 1, so that's our pi over 2. This one at pi, our coordinate is negative 1, 0, and at 3 pi over 2, our coordinate is 0, negative 1. Now this is going to become important when we're graphing. The other values that we would look at here would be the values that are the halfway in betweens. So if we think of our, if we were to cut this in half and just add, I'm just going to do this in another color. I'm going to go purple on top of that. Pretend these are exactly in half. So this value here, this would be at pi over 4. If you were to draw this in as a triangle, this would be our 45, 45, 90 triangle. This measurement here, this would be pi over 4 here and there. So this would be our 1, 1, and our square root 2. So if we think of this as coordinates, this would be 1, 1. So we have then 2 pi over 4, 3 pi over 4 would be here, and our coordinate there, if we think about our 45, 45, 90, would be negative 1 on the x and positive 1 on the y. This one here, which would be 5 pi over 4, our coordinates would be at negative 1, negative 1. And here at 7 pi over 4, our coordinates would be, if we were to draw this in as our triangle, we'd have a positive 1 on the x and negative 1 on the y. Now this is going to matter when we start to do our graphing, what these values are. Because the thing we have to keep in mind when we're doing these is when we're finding the tangent, it's always the y value over the x value. So when we're filling in our table down here, we care about those because they're going to help us find our answers. So if we look at the first one, we're going to do a table of values. We're going to, and I didn't put in the 30, 60, 90 in here. We'll just fill those in as we're going along. I just put in the 45s just so the graph, my circle itself didn't get too confusing. You always have my unit circle in the classroom that you can take a look at and see those values there. So at 0 degrees, right here, 0 degrees, if I punch it into a calculator or if I use it as an exact value, it's y over x, so that's going to be 0 over 1, so that's just 0. Tangent of 30 degrees. So if I think of my, and I'm just going to draw this in here, if this is 30 and this is 60, and that's my 90, I know that this is my 2, this is my 1, and sorry, whoops, this is 1. I have those mixed up, don't I? And this is square root 3. I didn't draw that in there very nice. This should be square root 3 opposite of the 60. And 1 opposite of the 30. My sides obviously aren't in proportion. So if I'm looking at tangent of 30, opposite over adjacent is going to be 1 over square root 3. If I put that to 2 decimal places like it says in there, this would be decimal 58. 45 degree angle. So 45 is up here. I have 1 over 1, so that's just a 1. 60 is opposite over adjacent, so that's going to be square root 3, which as a decimal is 1.73. 90 degrees up here is going to be 1 divided by 0. Well, 1 divided by 0 will get an error on your calculator. We call that as undefined. And sometimes what they write that as, it's the circle with the slash through it, just to show there's no solution. So 120 degrees is going to be, if we think of 120, our reference angle is 60 degrees for that one. But 120 is going to be over here in quadrant 2, and it's negative in quadrant 2, so that's going to be a negative square root 3, or a negative 1.73. 135 degrees, that's our 3 pi over 4, so that's going to be 1 divided by negative 1, so it's a negative 1. 150 degrees is part of our 30, 60, 90 with a reference of 30. So tangent is going to be that 1 over square root 3, but it's in quadrant 2, so it's negative. So it's negative 1 over square root 3, or negative decimal 53. And then if I go to 180, I have 0 divided by negative 1, so it's just 0. So it says now that you note that after you reach theta is equal to 180, the values for tangents start to repeat. So if I went down to 210, my reference angle, I would be here in quadrant 3, would be 30 degrees. So I'd be doing tangent of 30, which would be 1 over square root 3. Tangent is positive in there, so it's going to be a positive 1 over square root 3. So it's that decimal 58. So you can see I'm going to start repeating because I'm using the same reference angles. This, in the first box I used a 45, well 225 has the same reference angle of 45 degrees. So this one, if I calculate, it would be a 1. This one would be square root 3, or that 1.73, 270. My reference angle for that one is 90, so that again is an undefined. Negative 300 is negative square root 3. 315 would be a negative 1. This would be my negative 1 over, whoops, square root 3. And then I'd be back to 0 again. And then it would repeat again. So after that 360, I would have 390, which would be 1 over square root 3. And then I would have 405, which would be 1, and so on and so on. just have to pause for a minute. Okay, so it says the most interesting behavior of the tangent function occurs as theta approaches angles such as 90, 270, 45, etc. So if we look at those on that chart, at 90 degrees it was undefined, at 270 it was undefined. If we continued at 450, it would be undefined. So it says let's investigate the values of tangent theta for angles very close to 90 degrees. So for convenience, we will use degrees for these measurements. So all I'm going to do is just put in the values for these. These were calculated just using your calculator and just going tangent 70, tangent 80, tangent 89, so on, but making sure your calculator is in degree mode. So tangent of 70 is 2.75. 80 degrees is 5.67. 89 degrees is 557.29.29. 89.9 is 572.96. 89.99 is 5,729.57. So if you kind of notice what's happening, except for this first one, my decimal place is just sort of moving over. And because of rounding, my answer is a little bit different. But if you look here, I had 5729 for 89, 57296 for 89.9, then 572.957. So it's just a matter of rounding. So then it goes that the pattern would be, this would be 57,295.72. 89.9999, which is really close to 90, has 572,957.2. And I can continue going on this, keep adding nines on to the end of here, and what happens is this number is getting larger and larger. So it's getting closer and closer. It would go on forever. It would go on to infinity. Once I hit 90, if I put 90 or tangent 90, I'm going to get that error. If I go 90.0001 and put that into my calculator, I get a negative value. Negative 172,957.2, which coincidentally is the exact opposite of this one. I've gone from a large positive value to a very large negative value. And then as I move my decimal place one closer, my decimal moves here. So when I get to 100, it's negative decimal 5, 6, 7. I jump to 110. It's negative 2.75, which is the exact opposite of the tangent of 70. So if I look, my number here is getting a really large negative value. It's going to negative infinity. It'll go on and on and on, the more decimal places that I had there. And as my number is increasing, I'm getting closer to 0. So if I had tried negative 200 in there, I would have a small number close to 0. So I'm not sure what it is exactly, but it'd be a negative 0 decimal something. So it says, what happens to tangent theta as theta gets closer and closer to 90 degrees? Well, your number is getting larger. And it's basically moving on to infinity. What happens to tangent theta when you jump over the 90 and start at a larger decimal value? We go from a really small number and eventually make our way to 0. So it says this is asymptomatic behavior around theta is equal to 90 degrees, where the tangent is undefined. So it's a special case. It's going to get closer and closer and closer and closer and closer as your number gets closer to 90. It's going to get really close to that number, and then it's going to jump because it can't equal 90. As soon as it equals 90, it's an undefined value. And then if you jumped over to the other side and started putting decimal values onto that 90, then it's going to start moving further and further away and get closer to 0. So it says using this information we can sketch the graph. So based on the chart and this information here, we can graph our y is equal to tangent theta. So the first thing that we're going to look at is the fact that at certain values, 90, 270, and then as we got bigger, that 450 and so on, we had undefined values. So at those points, we have to put in what we call our asymptotes, and we've used asymptotes before. So at asymptotes, it means that at some values, we are not going to be able to cross that line. And it works the same for negative values. So then if I use the other values from my chart, when theta was, equal to 0, I had a 0 value. When theta was 30 degrees, which is right here, it was at decimal 5/8, so it was just a little bit more than halfway above. When it was at 45 degrees, so that's going to be, if this is 90, this would be 30 degrees here and 60 degrees here. At 45, it was at 1. At 60 degrees, it was 1.73, so that's almost at 2. And then based on my chart that I just did there, the closer that I got to 90 degrees, the higher this went, the closer it went to this line, but it never ever touches that line. So you can just put a dot almost on top of that asymptote, but not quite touching it. So then this side would look like that. So then at 120 degrees, which is right here, my value was that negative 1.73, so it's 1 and almost 3/4 of the way down. At 135, which will be halfway in between here, it was at negative 1. At 150 degrees, it was at negative decimal 5/8. So 150 is going to be here. That's just a little bit more than halfway. And then at 180, it went to 0. So then again, if I went closer to that 90 degrees, that 90.01, it's going to be really close to there. Oops, pretend that this is going right through my dots. So it looks like that. So 180, I had 0. 210 degrees, I had that 1 over square root 3, so it was at decimal 5/8. Oops, I'm a little over there. So there, that's a little bit better. At 225 degrees, I was at 1. At 240 degrees, I was at square root 3, which was like 1.73, so that's about there. And then my next value at that 180, I wouldn't be touching, but I would be getting close. So it would do that. And then as I go to repeat my values, it's going to do the same thing. So at 300 degrees, it's at negative square root 3. So that's right here at that decimal 5/8. At 315 degrees, it's at negative 1. Oops, what did I do here? I think I got something. Oops, I'm on the wrong page. That would be why. $270, this would be 300. 315 would be negative 1. Oh, that's why it should be over more. And this here would be, whereas I can't see my numbers here, 180, 270. So this would be 360 here. So 360, I'm at 0, and then I'd be going So following the same pattern as I did there, 0.58, and then again about right there, and then I'd have one there. So you can see the pattern, the way it goes. So to the right of the 0, it's going up. To the left of the 0, it goes down. So then this one here, I could continue going this way in the negatives here. So I'd be about there, 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 and then I would be somewhere down there. So if I was 0 at 180, I'd be 0 at negative 180, and then the same pattern would continue here. What is this one about right there? So to the right, it goes up. To the left, it goes down. And of course, my dots are just approximate. So that's what a tangent graph would look like. So the next, and I'm not going to flip yet, I'll write them in, but it says, what is the period of this tangent function? So how often is this repeating? So I have 1/2 is going up, 1/2 is going down. That repeats if I look in between my asymptotes here between 90 and 180, or sorry, 270. So that's 180 degrees. If I looked at in this part of the graph here, went between negative 90 and 90, well, that's a distance of 180 degrees. So what is the amplitude of this? The amplitude is what is the maximum or minimum value of this? Well, this continues on the y. It's going up forever. Depending on what value we plug into that tangent is going to depend on how high it goes up. So the period of this function is 180 degrees, or pi. What is the amplitude of this tangent function? There is no amplitude. Okay, the next question says, what are the equations of the asymptotes? So the asymptotes are the dotted lines, and they started at 180, and then they moved to, excuse me, sorry, at 90, and then they were at 270. So every 180 degrees is where they are, but it started at when theta was 90. So they are odd multiples of 90. Okay, so by odd multiples, what that means is I'm going 90 times 1. Well, that gave me my first asymptote. 90 times 2 is 180 degrees. I didn't have an asymptote there. 90 times 3, the next odd multiple, is 270 degrees. That gave me an asymptote. 90 times 4, whoops, I don't want to write that one down. 90 times 4 was 360. That was a 0 value. 95 times 5, though, would be 450, which is also an asymptote. So it works the same as if this was saying pi over 2. Pi over 2 times 1, pi over 2 times 3, pi over 2 times 5, and so on. So to write that, to write this as kind of an equation, what we say is theta is equal to odd value. If you remember from doing problem solving, if it says you need odd multiples, you're using 2n plus 1, because that will always give you an odd number. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. So this is just the equation for finding an odd multiple. And then we're just going to times that by 90 degrees. Or if you're thinking of this in terms of radians, it'll be 2n plus 1 times pi, or pi times 2n plus 1. Sorry, not pi, pi over 2, because it's 90 degrees. Okay, what are the x-intercepts? Well, the x-intercepts were at 180 degrees, and then they were again at 360 degrees, and then they would be at 540 degrees, and so on. So they're at every 180 degrees. So any multiple of 180. So you're at 180 times n. Or we could say this would be x is equal to pi times n. And n is an element of integers. Okay, so the next part says construct the graph of y is equal to tangent x, where x is any real number. So basically what we're doing is just a repeat of our last graph. Instead of using our degrees, though, 90 degrees and so on, we're going to be using pies, or instead of using degrees, we're using radians. So we know at every odd multiple of 180, we have a, what's that word I'm looking for? An asymptote. Sorry, an odd multiple of 90, not 180, pi over 2. So I have an asymptote here. I have an asymptote here. 1 pi over 2, 3 pi over 2, 5 pi over 2. Then going the other direction, whoops, negative pi over 2, negative 3 pi over 2, and then negative 5 pi over 2. My x-intercepts occur at 180 times n. So 180 times 0 would be here, 180 times 1, 180 times 2. I could do 180 times 3, but it'd be right on the line. Going the other way, 180 times negative 1 would be there, 180 times negative 2. I just have to pause for a second. Okay, so once you have your x-intercepts plotted in there and your asymptotes, then you want to look at, okay, what's just a nice simple value to plot? Well, when theta was equal to pi over 4, so when we did tangent of pi over 4, and then any multiple of that, we had a value of 1. So it's either going to be a positive 1 or a negative 1, depending on if we're looking which quadrants it's that reference of pi of 4 is. If it's in quadrant 1 and 3, it's going to be positive. If it's in quadrant 2 or 4, it's going to be negative. So all that means is when you go to plot these, you're always going to have your positive, your pi over 4 is at 1, negative pi over 4 then is going to be at negative 1. At, I just want to see where 5 pi over 4, which would be here, it's going to be a positive value, because 5 pi over 4, if you think about that, that's going to be here, so it's in that quadrant. But at 3 pi over 4, which would be here, it's going to be negative. So you're just alternating on those pi over 4 multiples between a positive and a negative value. And then the same thing on the other side. It's going to go positive, and then negative, positive, and negative. And then if you want to, you can plot that other point up near infinity at the top there, but you don't need to. Basically, the only thing you need to know then is that my graph is going to get closer to the asymptote, but never touch it. So that's a simple plotting of tangent of y is equal to tangent x. Mark in your asymptotes, mark in your x-intercepts, do your, simplest plot, in this case pi over 4. So features of the graph y is equal to tangent x. The wavelength, okay, wavelength is the same as your period, well that's just pi. My range for this is just y is an element of real numbers. It's going to go up forever and down forever. It's going to be decimal numbers. It's going to be fractions. Domain, well, my x is an element of real numbers as well, but it is not, x cannot be an odd multiple of pi over 2. That's a long way to write that. That's the same thing as we just figured out in that one. Every odd multiple of pi over 2, so pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, going negative, the same thing, is going to have an asymptote. So the way we write that instead of that is we say x is an element of real numbers, and then put a comma and say x is not equal to odd multiple, 2n plus 1, times pi over 2. My asymptotes then, the equation for the asymptotes is go hand in hand with the domain. But instead of saying that not equal to, my asymptote, this is the equation for it, is just x is equal to 2n plus 1 times pi over 2. The zeros are the x-intercepts, and that just, it didn't get cut off here, happened at every pi times n. Okay, and I'm going to pause here. This gives you just the general gist of graphing them. And then the second part, what I'm going to do is the transformations of the graphs of y is equal to tangent x. So what happens when you put in those shifts, the h, the k, the a, and the b.